And now in this lecture I'll answer two questions. In the first question we find out the radius of this circle, and in the second question we find out the area of this circle using two different methods. So we start with the first question. In the drawing we have a circle and we have also the right triangle ABC. Side AB equals to 3 units in its length. This is angle ABC, that is right angle. This is line segment AD. That is equals to 3 units in its length. This is the short line segment DC. That is equals to 1 unit in its length. Again, our task is to find out the radius of this circle. So first of all, we can implement rule 25 in our drawing. Repeat quickly on rule 25. Rule 25 is also called tangent second theorem. According to rule 25, if from a common start point P, we will draw a tangent to the circle that is actually tangent PA, and the line segment that is actually second PC. This is second PC. That cuts the circle. That cuts the circle in 2 points, point B and point C. So in this drawing, the following equation is true, that PA square equals to PB times PC. Again, PA square equals to PB times PC. So we can actually implement rule 25 in our drawing. Why? Because in our drawing, if we focus on this common start point C, from this common start point C, we have tangent CE, that is tangent to this circle at point E, and we also have second CA, that cuts the circle at 2 points, D and A. So actually all the requirements of rule 25 are satisfied, and therefore we can implement here rule 25. So I write it down. If we focus on the common start point C, the following equation will be true, that CE square equals to CD times CA. And again, according to rule 25, if we focus on this common start point C, the following equation will be true, that CE square equals to CD times CA. CE is the missing side, so we leave it as it is. So it is CE square equals to CD. CD is 1 times CA. CA in total equals to 1 plus 3, that is 4. So in total we found out that CE square equals to 1 times 4. 1 times 4 is 4. So CE square equals to 4. Here we take a root out of this equation, and we get that CE, the length of tangent CE, is equal to 4, that is 2. CE equals to 2 units in its length. This is line segment CE, that equals to 2 units in its length. In the next step, we will implement the Pythagoras theorem on the right big triangle time ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse AC equals to 3 plus 1, that is 4. Side AB equals to 3 units in this length, according to what is given in the question, and BC is the missing side. Here by PT is the relation for Badala story. So actually, this is the right triangle ABC, is according to the original line, and this right triangle ABC according to the Pythagoras line, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16. And it equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9. Plus BC squared. BC is the missing side, so we leave it as it is. So in total we should find out that 16 equals to 9 plus BC squared. Here we subtract 9 from the equation, and we get that 16 equals to, that 16 minus 9 is 7, so 7 equals to BC squared. Here we take out all of this equation, and finally we get that BC equals to the square root of 7 units in its length. So actually this is side BC. Is equals to the square root of 7 units in its length. What is the length from this missing line segment BE? B equals to BC minus AC. So I did on BE equals to BC minus AC. So BE equals to BC square root of 7 minus EC. EC is 2. So in total, we actually found out that B equals to the square root of 7 minus 2 units in its length. This is the line segment BE is equals to the square root of 7 minus 2 units in its length. In the next step, we will join points O and D together by a straight line. According to what is given in the question, point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle. We define the radius of this circle as R, so OE equals to R. Is the radius of the circle. the radius OE is equals to R. The radius OE is on to point E. This is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we will do another construction. That is to say, from point O, that is the center of this circle, we will draw perpendicular on AB. Again, from point O, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O inside AB. This point is point L. By doing this construction, we can do quadrilateral OLCE. In quadrilateral OLBE. This letter is B. In quadrilateral OLBE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrilateral LBEO we have 4 right angles, and therefore according to rule 5, quadrilateral LOBE is a rectangle. So it has 4 right angles. Now let it down. This is quadrilateral LOEB, that is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle LOEB, side OE is equal to the opposite side LB, but OE is R, therefore the opposite side LB must be also equal to R units in its length. According to the sum rule, in the sum rectangle LOEB, side BE must be equal to the opposite side LO, but BE is square root of 7 minus 2, therefore the opposite side LO must be equal to the square root of 7 minus 2 units in its length. So it is known LO equals to the square root of 7 minus 2 units in its length. What is the length of this? This is 970 AL. AL equals to AB minus LB. Again, AL equals to AB minus LB. So write it down. AL equals to AB minus LB. So AL in total equals to AB is 3 according to what is given us in the question. Minus LB, LB is R. So in total AL equals to 3 minus R units in its length. This is the missing 970 AL, that is equals to 3 minus R units in its length. In the next step, we will join points O and A together by a straight line. Point O is the center of this circle, point A is the point on the circle itself, therefore OA is the radius of this circle. This is equals to R according to our definition. In the next step, I'll copy the right triangle ALO in the new quadrant. We implement the Pythagoras theorem on this right triangle, triangle ALO. We implement the Pythagoras theorem on the right green triangle, triangle ALO. Here by PT is the abbreviation of Pythagoras theorem. So actually this is the right green triangle ALO that according to the original domain. This right triangle ALO, according to the Pythagoras theorem, AL square, AO squared, that is the square of the hypotenuse, equals to AL square plus LO square. So write it down. AO squared, that is the square of the hypotenuse, equals to AL square plus LO square. AO is R, therefore AO square is R square, and it is equals to AL square. AL is 3 minus R, therefore AL square is 3 minus R squared plus LO square. LO is square root of 7 minus 2, therefore LO square is square root of 7 minus 2 squared. So in total we should find out that R square equals to 3 minus R squared plus 7 minus 2 squared. So R square equals to 3 minus R square equals to 3 squared, that is 9, plus R square minus 2 times 3 times R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared in total equals to 0.417. So in total we should find out that R square equals to 9 plus R square minus 6R plus 0.417. Here we have R square on both sides of this equation, so R square gets cancelled. After you cancel R square, this side of the equation we left with nothing, that is to say 0. While on the other side of the equation we have 9 plus 0.417 is 9.417 minus 6R. So in total we should find out that zero equals to 9.17 minus 6R. Here we add 6R to this equation, and we get that 6R equals to 9.417. Here we divide this equation by 6, and finally we get that R equals to 9.417 over 6 is 1.57 units. So if you found out that the radius that you are looking for in this question, that is the radius of this circle, is equal to 1.57 units in its length. So we finish with the first question. In the next step I will present you the second question, and we solve the second question by using two different methods. Our task in the second question is to find out the area of this circle. So we start with the first method. In the drawing we have a circle. This is line segment BC, this equals to 6 units in its length. This is chord BA, that equals to 13 units in its length. This is line segment CD, that equals to 18 units in its length. Those two angles, they are both right angles. Again, our task is to find out the area of this circle. Those two angles that are right angles are defined as one-sided interior angles. The sum of those two angles is 90 degrees plus 90 degrees is 180 degrees, and according to rule 27, if the sum of two one-sided interior angles is equal to 180 degrees, then they must be located between parallel lines. So those two angles must be located between parallel lines because the sum of those two angles is 180 degrees. So those two angles must be located between the parallel lines BA and CD. That is to say, chord BA is parallel to line segment CD according to Rule 27. So write it down. BA, chord BA is parallel to line segment CD according to Rule 27. In the next step, we define the center of this circle. This point is point O. From the center of this circle, that is to say from point O, we will draw perpendicular on CD. So actually, this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and CD. This point is point M. In the next step, we will extend the perpendicular OM by straight line until it touches chord BA. Repeat again, we will extend the perpendicular OM by straight line until it touches chord BA. So actually, and we will define the touching point of the extended perpendicular OM with chord BA. This point is point N. According to Rule 27, line segment CD is parallel to chord BA, and therefore the extended perpendicular OM must be also perpendicular to chord BA because of the fact that line segment CD is parallel to chord BA and OM is perpendicular to line segment CD. The extended perpendicular OM must be also parallel to chord BA, must be also perpendicular to chord BA because they are parallel to each other. So actually, this angle also equals to 90 degrees, and this angle equals to 90 degrees according to the rule that I mentioned, that the perpendicular to CM must be also perpendicular to chord BA because they are parallel to each other. Okay, so in quadrilateral C, B, and M, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. Likewise, if we focus on the ON as a perpendicular, it is absolutely a straight line. So if we focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is a right angle according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So inside quadrilateral, the upper quadrilateral BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral BCMN, we have 4 right angles, and according to Rule 5, quadrilateral BCMN must be rectangle. So quadrilateral BCMN is a rectangle because it has 4 rectangles. Here we can implement rule 19. Repeat quickly rule 19. According to rule 19, the perpendicular from the center of a circle towards any chord bisects the chord. In the drawing we have a circle, and point O is the center of the circle. According to this rule 19, the perpendicular OM to chord AB bisects chord AB. That is to say, it divides chord AB into 2 halves. AM equals to MB. We can implement rule 19 in our drawing. Why? Because in our drawing, from the center of this circle, that is to say from point O, we have perpendicular ON to chord BA. Again, from the center of this circle, that is to say from point O, we have perpendicular ON to chord BA. And according to rule 19, perpendicular ON bisects chord BA. BA in total equals to 13, and perpendicular ON bisects chord BA. So the first half BN must be equal to 13 over 2, that is 6.5 according to rule 19. And the second half NA must be also equal to 6.5 units in its length, according to rule 19. So in rectangle BCMN, the opposite sides are equal to each other. So side VN is equal to the opposite side CM, but BN is 6.5. Therefore, the opposite side CM must be also equal to 6.5 units in its length. In the next step, we'll do another construction. That is to say, from point A, we will do perpendicular on CD. Again, from point A, we will do perpendicular on line 7 CD. So actually, this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A and CD. This point is point L. By doing this construction, we created the quadrilateral MNLA. Inside quadrilateral MNLA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral MLA we have 4 rectangles, and therefore according to rule 5, quadrilateral MNLA is a rectangle. Because it has 4 rectangles. So write it down. But we also know that the opposite sides of rectangle are equal to each other. So in the lower rectangle MNLA, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this missing 97 LD? From the drawing it is very easy to see that, that LD in total equals to CD minus CL. So write it down. LD equals to CD minus CL. So LD equals to CD. CD is 18. According to what is given in the question, minus CL. CL in total equals to 6.5 plus 6.5, that is 13. So in total, LD equals to 18 minus 14, that is 5. So LD equals to 5 units in its length. This is the missing short line segment LD, that equals to 5 units in its length. In the next step, we will extend line segment DC by a straight line until it touches the circle. And we will define the touching point of the extended line segment DC with this circle. This point is point T. By doing this construction, we created chord TD. This is chord TD. So in the drawing we have from the center of the circle, that is to say from point O, perpendicular OM to chord TD. Again, this is perpendicular OM to chord TD. And according to rule 19, a perpendicular from the center of the circle towards any chord bisects the chord. So according to rule 19, perpendicular OM to chord TD bisects chord TD. If OM bisects chord TD, it means that TM equals to MD. So write it down. According to rule 19, TM equals to MD. Repeat again, according to rule 19, TM equals to MD. But MD equals to 6.5 plus 5. 6.5 plus 5 is 11.5. So we can write that MD equals to 11.5 units in its length. MD equals to 11.5. And from this equation, TM equals to MD equals to 11.5, we will derive that TM is also equals to 11.5 units in its length. This is line 7 TM that equals to 11.5 units in its length. So from one side, TM equals to 11.5. But from the other side, TM equals to TC plus CM. Again, TM equals to TC plus CM. So it is not. So from the other side, TM equals to TC plus CM. So TC is the missing side, so limited it is, plus CM. CM is 6.5. And from this long equation, we will derive that 11.5 equals to TC plus 6.5. Here we subtract 6.5 from this equation, and we get that the missing 970C is equal to 11.5 minus 6.5 is 5. So we found out actually that the missing 970C is equal to 5 units in its length. This is the missing 970C that is equal to 5 units in its length. In the next step, we will extend 970BC by straight line until it touches the circle. And we will define the touching point of the extended 970BC with this circle. This point is point Q. By doing this construction, we're going to do code BQ. This is code BQ. Code BQ intersects with code TD at point C. Again, code BQ intersects with code TD at point C. So write it down. We actually found out that code BQ intersects with code TD at point C. So here we can implement rule 15. Repeat quickly on rule 15. According to rule 15, if code AB intersects with code CD at point O, then the following equation is true that AO times OB equals to CO times OD. So in the domain we have a circle. This is code AB that intersects with code CD at point O. So in this domain the following equation is true that AO times OB equals to CO times OD. AO times OB equals to CO times OD. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, code BQ intersects with code TD at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. According to rule 15, the following equation will be true that TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. So write it down. TC times CD equals to BC times CQ. Please again, according to rule 15, the following equation is true that TC times CD equals to BC times CQ. TC is 5 times CD is 18 and it is equals to BC is 6 times CQ. CQ is the missing side, so believe it is. So in total, if you found out that five times 18 equals to 6 times CQ. Here we divide this equation by 6, and we get that CQ, the missing side CQ, equals to 18 over 6 is 3, and 3 times 5 is 15. So the length of the missing side CQ is equal to 15 units. This is 97 CQ, is equals to 15 units in its length. In the next step, we will join points Q and A together by a straight line. So we join points Q and A together by a straight line. So here we can implement all 5. I'll click on all 5. According to all 5, any peripheral angle is equal to 90 degrees in its size must subtend on the diameter of the circle. In the drawing we have a circle. This is peripheral angle MAN, that is equal to 90 degrees in its size, and therefore according to this rule, all 5 peripheral angle MAN must subtend on the diameter of the circle. And indeed, peripheral angle MAN, that is equal to 90 degrees in size, subtend on chord MN, that is the diameter of the circle. So according to this rule, all 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. We can definitely implement rule 5 in our drawing. One, because in our drawing, this is peripheral angle ABQ, that is equal to 90 degrees in size, and therefore according to rule 5, peripheral angle ABQ must subtend on the diameter of the circle. Peripheral angle ABQ subtend on chord QA, therefore chord QA must be the diameter of the circle according to rule 5. So write it down. So she found out that chord QA is the diameter of this circle according to rule 5. The diameter of any circle is twice as long as the radius. If we define the radius of this circle as r, then the diameter QA must be equal to 2r. So QA, this is called QA, is equals to 2r according to rule 5. In the next step, I'll copy the right triangle QBA in the new page, and we will implement the Pythagoras theorem on this right triangle QBA. This is side QB. This is equals to 15 plus 6, that is 21. This is side BA. This is equals to 13 units in its length according to what is given as the question. We just write off now that the hypotenuse QA equals to 2r. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle BQA that is going from the original drawing. This right triangle BQA, according to the Pythagoras theorem, QA squared, that is the square they are produced, equals to QB squared plus BA squared. So write it down. QA squared, that is the square they are produced, must be equal to QB squared plus BA squared. QB is 21, therefore QA, the opposite QA is 2r, therefore QA squared is 2r squared, that is 4r squared. So 4r squared equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441 plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total we found out that 4r squared equals to 441 plus 169. 441 plus 169 is equals to 610. So 4r squared equals to 610. Here we divide this equation by 4 and finding that r squared equals to 610 over 4 is 152.5. So we found out that r squared equals to 152.5. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Okay, again, the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared, but r squared equals to 152.5. So we solve r squared this expression by 152.5, and we get that the area of our circle equals to pi times 152.5 square units. On top of some numbers, pi times 152.5 is equal to 479.09 square units in its size. So repeat again, we found out that according to the first method, the area of the circle it is equal to either 152.5 pi square units in its size, or in terms of numbers, the area of this circle is equal to 479.09 square units in its size. So we finished with the first method. In the next step, I'll present to you how to find out the area of this circle according to the second method. In the second method, we use with the things that we already found out in the first method. In the first method, we have already found out that this is 9 cm cubed, that is equals to 15 units in its length. This is the short 9 cm TC, that is equals to 5 units in its length. So we use with those two things that we already found out in the first method, in the second method. So here we can implement rule 26. Why can implement here rule 26? Because we have here chord TD that intersects with chord BQ at 90 degrees at point C. And whenever you have two chords that intersect with each other at a right angle, like in this drawing, you can implement rule 26. So repeat quickly on rule 26. According to rule 26, first of all, rule 26 is true in any circle. So in any circle, if two chords A, B, and C, D intersects with each other at a right angle, chord AB intersects with chord CD at 90 degrees. That is to say, at the intersection point, This is point O, they create 90 degrees with each other. So chord AB intersects with chord CD at 90 degrees. So in this drawing, the following equation is true. That AO square plus OB square plus CO square plus OD square equals to 4R square, and R is the radius of the circle. So whenever you have two chords that intersect with each other at a right angle, you can implement rule 26. Now a drawing chord AB intersects with chord CD at 90 degrees at point O, and therefore, according to rule 26, the following equation is true. That AO square plus OB square plus CO square plus OD square equals to 4R square, and R is the radius of the circle. So we can implement rule 26 in our drawing. As I already mentioned before, chord TD intersects with chord BQ at 90 degrees at point C. The intersection point occurs at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement rule 26. So write it down. I can find out that in our original drawing, chord TD intersects with chord BQ at 90 degrees, and their intersection point, that's actually point C, they create between them 90 degrees. Point C is their intersection point. Okay, again, I should find out that in our original drawing, chord TD intersects with chord BQ at 90 degrees at point C. So all the requirements for rule 26 are satisfied, and therefore we can implement rule 26. According to rule 26, the following equation is true. That TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared, and R is the radius of the circle. Repeating again, according to rule 26, the following equation is true. That TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. TC is 5, therefore TC squared is 5 squared, that is 25. Plus CD squared. CD is 18, therefore CD squared is 18 squared, that is 324. Plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. Plus CQ squared. CQ is 15. Therefore CQ squared is 15 squared, that is 225, and it is equal to 4R squared. So in total we found out that 25 plus 324 plus 36 plus 225 equals to 4R squared. 25 plus 225 is 250. And 324 plus 36 is 360 equals to 4R squared. 250 plus 360 is 610. So 610 equals to 4R squared. Here, we divide this equation by 4 and find again that R squared equals to 610 over 4 is 152.5. So if we found out that R squared equals to 152.5. Our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. So I write it down. The area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. But the radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. But we already found out that r squared equals to 152.5. So we substitute r squared in this expression by 152.5. So in total, we found out that the area of our circle must be equal to either pi times 152.5 square units in size. So in terms of numbers, the value of this expression is 479.09 square units in its size. So in both methods, we arrive to the same result. And again, in both methods, we arrive to the result that the area of this circle must be equal to either pi times 152.5 square units in size. So in terms of numbers, the area of this circle equals to 479.09 square units in its size. So we finish with the second method and with the second question. So in the next step, when we summarize the lecture, we'll start with the first question, of course. The first question, our task is to find out the radius of this circle. So in the drawing we have a circle, and this is the right angle ABC. This is angle ABC, this is right angle. Line segment AB, or called AB, equals to 3 units in this now. This is called line segment AD. This is equals to 3 units in this now. And this is the short line segment DC, this is equals to 1 unit in this now. Again, our task is to find out the radius of this circle. So here we can implement rule 25, because if we focus on the common standpoint C, from the common standpoint point C we have tangent CE, that is tangent to this circle is point A, it's point E. In addition, we have from the same common standpoint point C, we have secant CA that cuts the circle to points D and A. So all the requirements of rule 25 are satisfied, and therefore we can implement rule 25. According to rule 25, the following equation is true, that CE squared equals to CD times CA. Again, CE squared equals to CD times CA. So if we focus on the common standpoint point C, the following equation is true, that CE squared equals to CD times CA. CE is the missing sign, so we leave it as it is. So it is CE squared equals to CD, CD is 1, times CA. C in total equals to 1 plus 3, that is 4. So in total, if we found out that CE squared equals to 1 times 4, that is 4. So CE squared equals to 4. Here we took hold out of this equation, if I found out CE, the missing tangent CE is equals to the square root of 4, that is 2. CE equals to 2 units in its length. In the next step, we implemented the Pythagoras theorem on this right big triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the slopes of the perpendiculars. So actually, this is the right triangle ABC, this is according to the original drawing. According to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16. And it is equal to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing sign, so we leave it as it is. So in total, if we found out that 16 equals to 9 plus BC squared. Here we subtracted 9 from this equation, if I found out that 16 minus 9 is 7, so 7 equals to BC squared. Here we took hold out of this equation, and if I found out that BC equals to the square root of 7 units in its length. This is the missing side BC. This is equal to the square root of 7 units in its length. What is the length of this AC line segment BE? B equals to BC minus CC. Again, B equals to BC minus CC. So B equals to BC, that is square root of 7, minus CC, that is 2. So in total, B equals to the square root of 7 minus 7 is its length. The next step, we join points O and D together by side line. Point O is the center of the circle, point E is the point of the circle itself, therefore O is the radius of the circle. We define the radius of this circle as R, so O equals to R. The radius of E that is equals to R, the radius of E is known to point E, that is the point of tendency of tangent BC with this circle. And whenever your radius is known to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did another construction. That is to say, from the center of this circle, that is point O, we go perpendicular on AB. Again, from point O, we go perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point L. By doing this construction, we get the quadrangle OLBE. Inside quadrangle OLBE, we have 1, 2, 3 triangles. The sum of 3 triangles is 270 degrees, so 270 degrees plus the size of this 4 facing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrangle LOEB, we have 4 triangles. Therefore, according to rule 5, quadrangle LOEB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle LOEB, side OE must be equal to the opposite side LB. But OE is out, therefore the opposite side LB must be also equal to 1 unit in its length. Likewise, according to the sum rule, in the same rectangle LOEB, side BE must be equal to the opposite side LO. But BE is square root of 7 minus 2, therefore the opposite side LO must be equal to the square root of 7 minus 2 units in its length. What is the length of this missing line segment AL? AL equals to AB minus LB. Again, AL equals to AB minus LB. So AL equals to AB, that is 3, minus LB, that is R. So in total, AL equals to 3 minus R units in its length. We join points O and A together by side line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of the circle, that is equals to R. In the next step, I copy the right hand triangle ALO in the new page and implemented the Pythagoras theorem of this right triangle ALO. So okay, this is the right triangle ALO, the right hand triangle ALO that according to the original drawing, in this right triangle ALO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AL squared plus LO squared. AO is out, therefore AO squared is R squared, and it is equals to AL squared. AL is 3 minus 1, therefore AL squared is 3 minus 1 squared plus LO squared. LO is square root of 7 minus 2, therefore LO squared is square root of 7 minus 2 squared. So in total, we should find that R squared equals to 3 minus 1 squared plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared. 3 minus R squared equals to 3 squared, that is 9, plus R squared, plus 2 times 3 times R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared in total equals to 0.417. So in total we should find out that R squared equals to 9 plus R squared minus 6R plus 0.417. Here we have R squared on both sides of this equation, so R squared we can cancel. But we can set R squared on this side of the equation, we left with nothing, that is to say 0. And on the other side of the equation, we have 9 plus 0.47, that is 9.417, minus 6 R. So if we found out that 0 equals to 9.17, again 0 equals to 9.417, minus 6 R. Here we added 6 R to this equation, and finally found out that 6 R equals to 9.417. Here we divided this equation by 6 and finally found out that R equals to 9.417 over 6, that is 1.57 units. So if we found out that the radius of this circle, that is the radius that we are looking for in this question, is equal to 1.57 units in its length. So we finish with the first question. In the next step, I presented to you the second question, and we solve the second question in two different methods. In the second question, our test is to find out the area of this circle. So in the drawing, we have a circle. This is 97BC, that equals to 6 units in its length. This is called BA, that equals to 13 units in its length. This is 97CD, that equals to 18 units in its length. Those two angles are both equal to 90 degrees. Again, our test is to find out the area of this circle. So first of all, those two angles are both equal to 90 degrees. The sum of those two angles is 180 degrees. Those two angles are defined as one-sided interior angles. And according to Rule 27, if the sum of two one-sided interior angles is equal to 180 degrees, then they are located between parallel lines. The sum of those two angles is 180 degrees, and therefore they must be located between parallel lines. That is to say, chord BA is parallel to 97CD. Repeat again, chord BA is parallel to 97CD according to Rule 27. In the next step, we define the center of this circle. This point is point O. And from the center of this circle, that is point O, we do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point O and CD. This point is point M. In the next step, we extended the perpendicular OM by side line until it touches chord BA. And again, we extended the perpendicular OM by side line until it touches chord BA. We define the tangent point of the extended perpendicular OM with chord BA. This point is point N. And because of the fact that OM is perpendicular to CD, the extended perpendicular OM must be also perpendicular to BA. What goes, they are parallel to each other. And again, because of the fact that chord BA is parallel to 97CD, the perpendicular OM or the extended perpendicular OM must be also parallel to BA. Actually, because of the fact that OM is perpendicular to CD, the extended perpendicular OM must be also perpendicular to chord BA. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the rule that I mentioned. So here, we can implement Rule 19. Why? Because we have, from the center of this angle, that is to say from point O, we have perpendicular ON on chord BA. Again, from the center of this angle, that is to say from point O, we have perpendicular ON on chord BA. And according to Rule 19, the perpendicular from the center of this circle towards any chord bisect the chord. So the perpendicular ON bisect chord BA, according to Rule 19. BA in total is 13. Half of 13 is 6.5. So the first half BN is 6.5, and the second half NA is also 6.5 according to Rule 19. Okay, so here we have in quadrangle BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth angle must be equal to 90 degrees in its size. So in quadrangle BC and M, we have 4 right angles, and according to Rule 5, any quadrangle that has 4 right angles must be this rectangle plus a square. So relate to quadrangle BCMN, it's a rectangle because it has 4 right angles. So quadrangle BCMN is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in integral BCMN, side BN is equal to the opposite side CM. But BN is 6.5, therefore the opposite side CN, the opposite side CM must be also equal to 6.5 in its unit in its length. ON is perpendicular, so ON is a perpendicular, it is absolutely a straight line. So if we focus on the lower side of the straight line ON at point M, if the sum of the angles must be equal to 180 degrees according to all three. So which angles we have at the lower side of ON at point M, we have this angle that is right angle according to our construction, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. In the next step we did another construction, that is to say from point A we do perpendicular on CD. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and I say CD, this point is point F. But doing this construction we can do quadrangle MN and A. Inside quadrangle MN and A we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total the must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in its size. So inside quadrangle MN and A we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be at this right angle in front of the square. So we are left to quadrangle MN and A, so rectangle because it has 4 right angles, but we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MN and A, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be equal to 6.5 units, because they are equal to each other. So what is the length from this missing line segment LD? LD equals to CD minus CL. Read again, LD equals to CD minus CL. So LD equals to CD, CD is 18, according to this given equation, and minus CL. CL in total is 6.5 plus 6.5, that is 13. So in total LD equals to 18 minus 14, that is 5. So this line segment LD is equal to 5 units in its length. In the next step, we extended line segment DC by straight line until it touches the circle. We define the touching point of the extended line segment CD with this circle. This point is point T. By doing this construction, we can do code TD. So here we can implement again all 19. Why? Because we have perpendicular ON to code TD. According to rule 19, perpendicular OM to code TD bisect code TD. That is to say, TM equals to MD. And again, according to rule 19, TM equals to MD. According to rule 19, TM equals to MD. But MD equals to 6.5 plus 5, that is 11.5. So we can write here that MD equals to 11.5, and from this equation TM equals to MD equals to 11.5, we will derive that TM is also equals to 11.5. This is line segment TM, this is equals to 11.5 units in its length from one side, but from the other side TM also equals to TC plus CM. Because again, from one side TM equals to 11.5, but from the other side TM also equals to TC plus CM. TC is the missing side and CM is 6.5. And CM is 6.5. And from this longer equation, we derive that 11.5 equals to TC plus 6.5. 11.5 equals to TC plus 6.5. Here we subtract the 6.5 from this equation and find that TC equals to 11.5 from 6.5 is 5. Okay. This is the missing 970 TC, this is equals to 5 units in its length. In the next step, we extended 97 BC by straight line until it touches the circle. With again, we extend 97 BC by straight line until it touches the circle. We define the junction point of the extended 97 BC 15 circle. This point is point Q. By doing this construction, we created chord BQ. It intersects with chord TD at point C. Again, chord BQ intersects with chord TD at point C. So all the requirements for full 15 are satisfied, and therefore we can implement rule 15. Repeat again. Now I'm drawing. Chord BQ intersects with chord TD at point C. And according to rule 15, the following equation is true that TC times CD equals to BC times CQ. Again, according to rule 15, TC times CD equals to BC times CQ. TC is 5, CD is 18, BC is 6, and CQ is the missing sign. Repeat again. TC is 5, CD is 18, BC is 6, and CQ is the missing sign. So in total, we found out that 5 times 18 equals to 6 times CQ. Here we divided the equation by 6 and finally found out that CQ equals to 18 over 6 is 3, and 3 times 5 is 15. So CQ equals to 15 units in its length. This is 97 CQ, that equals to 15 units in its length. In the next step, we join points Q and A together by straight line. By joining points Q and A, we can do peripheral angle ABQ. Peripheral angle ABQ equals to 90 degrees in size. And peripheral angle ABQ subtend on chord QA. Again, peripheral angle ABQ subtend on chord QA. And according to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. Peripheral angle ABQ is equal to 90 degrees in size, and therefore peripheral angle ABQ must subtend on the diameter of the circle. Peripheral angle ABQ subtend on chord QA, and therefore chord QA must be the diameter of the circle. Repeat again, chord QA is the diameter of this circle according to rule 5. So QA is the diameter, is twice as long as the radius. If the radius is R, then QA must be equal to 2R. PQ equals to 16 plus PQ equals to 6 plus 15, that is 21. BA equals to 13, and QA equals to 2R. So in the next step, I copied the right triangle ABQ in a new page, and we implemented the Pythagoras theorem on this right triangle ABQ. Actually, this is the right triangle ABQ. That I copied from the original drawing. In this right triangle ABQ, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. QA is 2R, therefore QA squared is 2R squared. This is 4R squared, and this is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441. Plus AB squared. AB is 13, therefore AB squared is 13 squared, that is 169. So in total, if you found out that 4R squared equals to 441 plus 169. 441 plus 169 is 610. So 4R squared equals to 610. Here we divided the equation by 4, and we found out that R squared equals to 610 over 4 is 152.5. So if you found out that R squared equals to 152.5, our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Again, the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. But r squared is 152.5. So we substitute r squared here by 152.5. And finally found out that the area of our circle is equal to either 152.5 pi square units in size. In terms of numbers, it is equal to 479.09 square units in size. So we finish with the first method. In the next step, I present to you how to find out the area of this circle according to the second method. In the second method, we used with the things that we have we have already found out in the first method. In the first method, we have already found out that this is a 970Q that is equal to 15 units in its length. This is 970C that is equal to 5 units in its length. So here we can implement rule 26. Why? Because we have chord TD that intercepts with chord BQ at 90 degrees. So all the requirements for full 26 are satisfied, and therefore we can implement here rule 26. Okay, again. Now original domain, chord TD intercepts with chord BQ at 90 degrees at point C. Intersection point occurs at point C. So according to rule 26, if two chords intersect with each other at 90 degrees, then the following equation is true. That AO square plus BO square plus CO square plus DO square equals to 4R square. So in the domain we have a circle, and chord AB intersects with chord CD at 90 degrees at point O. Okay, between them at 90 degrees at the intersection point, that is point O. So in this domain, the following equation is true, that AO square plus OB square plus CO square plus DO square equals to 4R square. And R is the center of R is the radius of the circle. So we can implement rule 26 in our domain because chord TD intersects with chord PQ at 90 degrees at point C. So all the requirements for rule 26 are satisfied, and therefore we can implement rule 26. According to rule 26, the following equation is true, that TC square plus CD square plus BC square plus CQ square equals to 4R square. Okay, again, according to rule 26, the following equation is true, that TC square plus CD square plus BC square plus CQ square equals to 4R square. R is the radius of the circle. TC is 5, therefore TC square is 5 square, that is 25, plus CD square. CD is 18, therefore CD square is 18 square, that is 324, plus BC square. BC is 6, therefore BC square is 6 square, that is 36, plus BQ square, plus CQ square. CQ is 15, therefore CQ square is 15 square, that is 225. And this equals to 4R square. So in total, if you found out that 25 plus 324 plus 36 plus 225 equals to 4R square. 25 plus 225 is 250, and 36 plus 224 is 360. So in total, if you found out that 250 plus 360 equals to 4R square. 250 plus 360 is 610, so 610 equals to 4R square. Here we divided this equation by 4, and found out that R square equals to 610 over 4 is 152.5. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is R squared. So the area of our circle must be equal to pi R squared. But R squared is 152.5. So we substitute R squared by 152.5, and finally found out that the area of our circle is equal to either 152.5 pi square inches in size, or in terms of numbers, is equal to 479.09 square inches in size. So in both methods, we arrive to the same result, that the area of our circle is equal to either 152.5 pi square inches in size, or in terms of numbers, the area of this circle is equal to 479.09 square inches in size. Okay, thank you very much.